You ever look at a massive bridge or a skyscraper and just wonder, is it really solid all the way through? How do you even check for hidden dangers inside something you can't see into? Well, today we're going to get into that because the answer is pretty amazing. It's kind of like giving our buildings an ultrasound. I mean, just look at this. It's a huge concrete structure. And sure, it looks solid, but what if it's not? What if deep inside there are voids or cracks or weak spots just waiting to cause a catastrophic failure? So how in the world do you find a problem you can't even see without, tearing the whole thing apart?
Okay, so the first thing you're probably thinking is, well, let's just drill a hole and grab a sample, right? But here's the catch. That's what we call destructive testing. You're literally damaging the structure just to check on it. Plus, you only learn about one tiny spot. That's just not going to cut it. We need a smarter way, a non-destructive way. And that brings us right to the heart of this explainer. We're talking about technology that acts like a medical ultrasound, but for our buildings and bridges. Welcome to the world of non-destructive testing. The specific technique we're looking at is called ultrasonic pulse velocity, or UPV for short. And honestly, the name tells you almost everything you need to know. Ultrasonic, that's sound at a frequency so high we can't hear it. It sends a pulse of that sound through the concrete, and it measures its velocity, or its speed. It's literally a way to see with sound. So how does this whole thing actually work out in the field? Let's break down the mechanics of sending that signal and what we can actually learn from it. At its core, the principle is shockingly simple. An engineer takes two little sensors, they're called transducers, and places them on the concrete. One is a transmitter, it sends out that little sonic bing. The other is a receiver, just sitting there waiting to catch it. And the machine's whole job is to measure with incredible precision how long that journey took. And that one little measurement gives us the golden ticket, the pulse velocity. It's just the speed of the sound wave as it moves through the material. And that number, that single number, tells us the story of what's really happening deep inside that concrete. And the math behind it, it's not some crazy advanced calculus. It's something you probably learned in high school physics. Velocity equals the path length, which is just the distance between the two sensors, divided by the travel time. A super simple formula that unlocks a ton of complex information. Of course, you can't always get to both sides of a giant concrete wall, so engineers have a few different setups. Direct transmission, with sensors on opposite faces, that's the gold standard. It's the most accurate. Then you've got semi-direct, which is perfect for working around corners. And finally, indirect transmission, where both sensors are on the same face, is great for checking surface quality or finding out how deep a crack really goes. But hey, if it were that simple, anyone could do it. The real art and science comes in interpreting the results, because concrete isn't just a perfect, uniform block of stuff. In the real world, a whole bunch of factors can complicate the reading. An experienced technician has to be like a detective. They have to account for everything. Is the concrete wet? Because believe it or not, moisture actually speeds the pulse up. What kind of rocks are in the mix? And the big one, the one that causes the most headaches. What about the steel reinforcement, the rebar, that's in almost all modern concrete? This brings us to the single biggest challenge in UPV testing: steel. Sound pulses move through different materials at different speeds. Think of it like running on pavement versus running through thick sand. For a sound pulse, steel is like a superhighway, and concrete is more like a bumpy side road. So, on average, an ultrasonic pulse travels through good quality concrete at about 4 kilometers per second. That's our baseline. Keep that number in your head. Now look at this. That same pulse zips through steel rebar at nearly 6 kilometers per second. That's almost 50% faster. It's a massive difference. So you can probably guess what happens if the sound wave finds a rebar to travel along. And that's the crucial point. If the pulse takes a shortcut down a steel bar, the travel time will be way shorter than it should be. The machine calculates a really high velocity, and the operator might mistakenly think, wow, this concrete is incredibly strong, when in reality, the sound just cheated. Engineers have to be super careful to plan their tests to avoid this exact trap. But despite these challenges, when it's done correctly, UPV testing is an incredibly powerful tool. So let's look at how engineers use this data to build a really detailed picture of a structure's health. The basic interpretation is really straightforward. A high, consistent velocity means the concrete is dense, uniform, and in good shape. But if that velocity suddenly drops, that's a huge red flag. It means the pulse had to travel around something, and that something is probably a crack, a void, or a patch of weak concrete.
And this simple principle has a huge range of applications. Engineers use UPV to create these amazing quality maps of entire structures. They can estimate the concrete strength, though that needs a bit of calibration. And most critically, they can hunt for those dangerous internal defects and even measure the true depth of cracks they see on the surface. So it's clear that UPV is a vital piece of technology. But like any tool, it's not perfect. It has a very clear set of pros and cons that are really important to understand. On the plus side, it's non-destructive, it's fast, and it can find problems deep inside a structure. Can't argue with that. But on the other hand, it is an indirect method. It measures velocity, not strength directly. And as we saw, it's very sensitive to moisture and can totally be thrown off by that sneaky steel rebar. This really sums it up perfectly. UPV is considered an absolutely indispensable tool for monitoring the health of our infrastructure, but it's rarely used all by itself. It gives the best, most reliable results when it's combined with other testing methods, giving engineers a much more complete picture of what's going on.
Which leaves us with a final thought to chew on. We live in a world built on concrete, and a lot of that concrete is getting old. The ability to see inside these structures without destroying them is more critical than ever before. It really makes you wonder, what other invisible tools will we need to invent to keep our world standing strong?